Tell me when I have to start.
Just now.
Now, okay. So maybe we have to help. Okay, I will start. So to say, you can stop me in any moment to make question. I welcome question. So then, also because now is the second part, so then, so you will know more information. So then we arrive to the conclusion, first of all, that you have to study and data that are of very high quality because to have the issues. So this has changed everything in 2000. So before, the most important thing was to know the amount of dark matter in the galaxy. That's it. But after 2000, the idea is how this dark matter is distributed. So the result is this one. I show just one example, and then we will choose something more. Then the observed data, they were perfectly fit by coordinate distribution, and NFW distribution didn't really match the data. And you can see in this case, for this galaxy, which has been studied a lot, and by also different authors, and the result is you can see the discrepancy that you have from an NFW halo with the observed one. This is what happens in almost all disk systems studied until now. So you get this kind of discrepancy, and then we can study also more. Now we can study galaxies coordinated and see what happens. So here there are 3,500 galaxies which are being coordinated, and what is now? Because the issue is, here you have a fit, which doesn't go for NFW. But NFW has also the parameters, okay? So there are two parameters on the dark matter and one parameter on the luminous matter. So how these parameters are physically reasonable or not? So then we have, okay, prediction, and also from other information, for instance, the color of the galaxy, luminosity of the galaxy, and so on. And they will stay in this, let's say, plane, which is the blue one, bluish this. Then you can analyze, okay, 3,500 rotation curve of all kinds of galaxies, disk galaxies, low surface brightness, dwarf galaxies, luminosity, and so on, and plot the chi-square versus the properties, for instance, on dark matter, which is the mass and the concentration. Therefore, you see that if you are in lambda CDM scenario, all these points, they should stay right on the surface. We'll see that most of them, if not all of them, they stay very, very far from the surface. So therefore, when you fit the data with NFW, or you get a chi-square which is very bad, or you get a disk mass which is ridiculous, for instance, 30 solar masses, a galaxy with 30 solar masses, or you get a halo mass which is ridiculous, which, for instance, 10 to 14 solar masses, or you get a concentration which is not the one you find in simulations. So you should find 8, you find 25, okay? So therefore, even if the fit is correct, the mass model is not, because the parameters are totally unphysical. So the conclusion, both individual and so, that the dark matter halos that are present in spiral galaxies, in these galaxies of any kind, these dark matter halos have not a cusp at the center of their density. So this has nothing to do at the moment with dark matter. nature, but of course at a certain point one should also enter in the situation, what is the dark matter nature. This is now very well accepted, almost by all people, and there is called the cusp core controversy, no? Or cusp core problems for CDM. But these are not things that I like to define these, because when you should talk about controversy, whether you know the problem means that you already know the theory, no? So it's a problem for a theory. But I will see, especially if we talk tomorrow, that we are at the level that we have to work out the theory yet. Anyway, so the final thing for spiral galaxies is that you have the matter in all of them, this dark matter is not the one which is obtained by simulations in pure dark matter scenario. Then we go to elliptical, because we want to understand also in other galaxies. So, and here is more complex, because we do not know in elliptical galaxy what is the distribution of the tracer, okay? The tracer which we measure the dispersion velocity or the kinematical status, but we don't know if the tracer, because at difference from a spiral galaxy where the tracers stay in a disk, here they could stay in ellipsoid, they could stay in a spheroid, who never knows. And another important aspect is when you compare gravitational field with, let's say, energetic field from kinematics, you have to put different terms, because the motions on every single particle of the tracer, we are not talking about the matter, we are talking about the tracer which will give us the potential of the galaxy, gravitational potential of the galaxy. We don't know if the tracer move radially, move tangentially, and move in three directions, or move each of them differently. And so, therefore, this is very complex, because from the data we have not only to get the dark matter distribution, which is unknown, not only to get the star mass, the stellar mass, which is unknown, but also the dynamical status of your tracers. Okay? And this makes the situation extremely difficult, of course. And one simplicity that one has is that these galaxies, they are not anymore active. So then from the luminosity, you can get the disk mass quite easily. Okay? So you have in spiral galaxies or small dwarf spirals, then you have star formation now. So then from the luminosity, you cannot get what is the mass of the object, because it seems that you must know what happened now and in the past at the transformation from gas to luminosity, gas, star, luminosity, and this is very, very complex. Instead, all elliptical galaxies are dead, okay? So they, by a lot of time, actually this will be a very important aspect also from galaxy formation. But for us helps, and you see for instance that the color does not depend on the radius, okay, of the galaxy, so this means that there is one population of stars, and maybe the mass-to-light ratio can be obtained by the color of the galaxy. So we have, differently from spiral galaxy, the only advantage is this, that we have alternative ways to get the stellar mass of this spheroid. But the advantages ends here, because as I said, okay, so this is the equation, the master equation, that it is in the case of elliptical galaxy, So you see that you need to know not only how is distributed their tracer, for instance, the stars, or nebula, planetary nebula, or so on, but you have to know the anisotropy of the orbits, as I said. So if the orbits are more radial and rather than tangential. And also here, I made an assumption, so that, for instance, you don't have three-dimensional orbits. So the fact that you have dimensional, the orbits could be three-dimensional. So you have, this equation will have another three parameter. Okay, so in the case in which the the angular coordinates are similar, there is a symmetry of this, you have this equation. And of course, you have many unknown here, and so it's very, very difficult to solve this. Okay, so one has to find tricks in order to solve this equation. And in practice, okay, so this is the system, and that I don't enter in detail because, of course, it's just to show how, from observations, even in the case of isotropy, then the observed thing, which is the last one, this is observed, and we respect so the dispersion velocity on the sky, and then you want to know the mass, for instance, then you have to solve this certain equation, and therefore, even in the most simple cases, there is no direct thing. Okay, so this is what I want to say. There is no direct thing between velocity, mass, velocity, dark matter. No. You have to solve this to show what's going on. So, and of course, so when you see for instance here, the velocities and the dispersion velocities of one galaxies, okay, you cannot see if this galaxy has dark matter, let alone if the dark matter is a core or cusp. Okay, so this is the intrinsic difficulties, no, that have, let's say, this kind of objects. What happened? No. Okay. So, I cannot discuss about the elliptic galaxy without talking about the fundamental plane. So, dispersion velocity, luminosity, length scale are related. Okay? But I tell you this, that just to say that in this case everything is due to luminous matter. So these are related to how these galaxies are formed. There is very little information about dark matter, about this relationship. Certainly there is something, but not that you can get as, for instance, an Italy-Fisher relation, that is a similar relation in spiral galaxy. Why? Because spiral galaxies are very extended. So when you have at the end of the star, you are quite far away from the dark matter halo. These galaxies are very compact, okay? much compact than the spiral galaxies. So they are in the inner part where the dark matter is very small. So therefore all these properties, they are properties of themselves. So the luminous part of the component, certainly depending on the total gravitational potential, but develop such relationship that I think some of you knows, but this is more important for the history of the star formation and the history of the galaxy formation rather than from the dark matter. So this is why I put I would say that there are methods, a lot of methods that attempt to get dark matter in these galaxies. One is given by planetary nebula, that they stay in the outer part, okay? And again, they have a line, so they can give some information. And for instance, this is one case in one galaxy, so you have a sort of information about the kinematic status. But again, you can get, okay, so you can get these dispersion profiles, but again, you don't know much about this dynamical status of such particle, okay, at this planetary nebulae, and so it's very, very difficult to get any information from the dark matter from this. Okay, so now we have a completely different scenario and methods. So again, now we take help from the GR, and there is a phenomenon of GR, which is the weak lensing. This is quite interesting because it is macroscopic. One would say that the system is practically no GR. Okay, we have one galaxy, which is the density, the motions, so they are certainly Newtonian, and it is also the galaxy outside. But in this phenomenon, you get an enormous phenomenon given by this GR effect, which is called the weak gravitational field. So let's suppose that you have a galaxy here. Here you don't have a galaxy. This is the field of a faraway galaxy, but this gets amplified, but especially distorted when the line of the side passes through the galaxy. So we know from this distortion that we get here the gravitational potential of this galaxy. Okay, so this is the idea. And this is helpful because we know things, and in a way which is completely different than the way which I've shown until now. And this also, it is important because they show the existence of dark matter halos, that they are as extended as I do, extrapolating the internal dynamics outside. So these are extremely important. They don't give us too much about the inner parts. They don't give anything about what happens inside the galaxy, of course, but they are very, very helpful because it is a completely independent way to get the fact that you have dark matter in galaxies. Okay? And when it is done, the dark matter in the inner part is in agreement with the other part. Okay, these are the formulae that maybe you know. These are the formula that relates how the distortion that we measure of these galaxies as far away galaxies with respect to the gravitational potential in the galaxy. So we can do, okay, this and make some model with the data, so measure data and then models. Okay, again, the process here is big, very, very complex, because in this case, just to say, we have the signal to noise is 10 to minus 4. Okay, so dynamics, if correct, gives a phenomenon with signal to noise which is 10 to 5, 10 to 6. Here the phenomenon in individual point is, individual measurement is 10 to minus 4. So therefore you have to put together enormous amount of galaxies, and then when you are below the signal, as I think as perfectly said Martin earlier, you enter in a very, very complex thing, and there are, of course, difficulties by the noise, selections, and so on, so on. So then, at the end, you get this, but I would say, rather also the only thing that, until now, they say that there is dark matter extended, but they cannot really select by one model or the other. So if you have a cusped or cored profile. Okay, so you have also another method for elliptical galaxies, we are talking about elliptical galaxy, is the sense that sometimes this effect is even in more giant. This is the GR effect. You have Einstein ring when, you have a certain density and particularly surface density of this galaxy. So if there is a good alignment between the galaxy outside and the galaxy internal, you get this Einstein ring that gives us another information. Again, important, but not decisive. The only thing that they can do here is the fact that the total density, mass plus density, dark matter, is constant as function of radius. Okay? So this is the total density goes like r minus 2 so the velocity, the so-called circular velocity correspondent is constant. So in this case is what is thought to be in spiral galaxy. So in elliptical galaxy we really find that the so-called circular velocity is constant, or better, the total density goes like radius to minus 2. This is one result, but not much explanation. So again, we have finished about the elliptical galaxy. Of course, I don't give much merit of this, because I should have given much more merit, because of course there are enormous amount of studies about this. But these studies only they cannot give much about the dark matter profile, the dark matter nature in those objects. And at the end of the game, they learn a lot about the distribution of matter, if it rotates, so about the stars and the spheroid, we have learned a lot of things, but as this, we don't know much. Now we go to the dwarf spheroidal. This is slightly different. What is a sort of elliptical galaxy, but the point is that you don't have a fluid like the dark matter. You have single points. So we get here, for instance, this is you can see each of them is a star. Okay, each of them is a star. So therefore, it can help a little more to do the mass modeling, because you don't have, at least where is the star that we are saying. In the elliptical galaxy, you don't take the measurement in places, but you take the measurement over a tube, which stays over the distance of the galaxy. From the first star out to the last star in the site, in the line of the site. Here we have slightly better situation, so we can hope that we can solve better the equations. First of all, it's interesting to say that the luminosity of this galaxy are similar to the luminosity of globular clusters, but their size is 2 or 3 times more. So you see that they must have some other component which puff up the size of those galaxies. So the distribution of the dispersion velocity, was obtained only in the 80s. The first was with 3 stars, so the average made by 3, and dispersion velocity can be done. So it's the minimum number of stars to do a dispersion velocity, and also because, the signal is in this case, the signal is very, very low. And in the past years, we are get much more data. So we got for galaxies now 1,000 independent measurement. Okay? And so certainly the idea, this is something about 10 years ago. So 10 years ago, the data weren't not able to prove much, in the sense that, the first order, if you put anisotropy equals 0, so which, by the way, could be the best way, you get that you have a correlate distribution. But if you are able, or if you do a change in the anisotropy in a special ways, you can get that also NFW profile can get the distribution. Here, another advantage that we have is that the stars do not enter in the gravitational potential. So they are really point masses. So therefore, you don't have 3 parameters, you have only 2 parameters. But again, we still don't know the dynamics of stars. Although being, let's say, single stars, the idea of isotropic motions is much more simple, and it is reasonable much more than in elliptical galaxies, where then you absolutely don't know the status of motions of the disk or the spheroids, because the spheroids is the outcome of formation, complex formation, and so on, and so it could be really very, very complex. In this case, we are single stars, and so at the end, the idea that you have everything is isotropic, especially when you put together many measurements, is okay. But still, if you want to change the anisotropy, so saying that these tracers, not the dark matter, the dark matter can be completely isotropic, but the tracer could be that the one which stays at the center, they prefer to go radially. The one which goes at the outer part, they prefer to go tangentially. In the middle, they go in another way. So if you, say, build a particularly profile, you can reproduce this. So you can reproduce this using standard, using a constant anisotropy, and colored distribution, so it seems simple, or you can use an ad hoc distribution of the dispersion velocity and distribution of anisotropy of the dispersion velocity, and assume NFW profiles. So, in other way, if for you is no problem in adding a few parameters, you can get the data also with the NFW profile. Now, coming back to the observed, so we take the simplest one, and we can make a sort of analysis in this way. So, therefore, you have, as I said, in spiral galaxies, a relationship which relates the core radius to the central density and of dark matter. So this is what you get from normal spirals. When you get this from dwarf spheroidal, you get they stay almost in the same line. So this is particularly important because if, let's say, is the analysis of assuming constant anisotropy is wrong, you will find this completely random. Okay? The fact that they stay on the line is a support to say that also this object, they have a core. And, after 10 years, the situation is still almost in this case. There have been found other ways to show that it's more likely that these galaxies have a core rather than a cusp. But still, if you insist in the cusp and you are able to have ad hoc assumption, is not able to rule out NFW profiles in these objects. Okay? And like instead, it happens in spirals. In spirals, anything that you can find, you cannot get NFW profile. Here is possible to have. Although many people, they are thinking that you have to, is not likely that it is. So this case, normal elliptical galaxies, the situation is completely open. For dwarf spheroidal is going to have chorus distribution. Although also here is open. What it is interesting is when you do for all galaxies, and then you study also some elliptical galaxy which you can do some modeling, and which is very, very small number. But when you compare the quantity, which is rho 0 R 0, rho 0 R 0 means the central surface density of the dark matter, with the core radius, with the magnitude, for instance, and you see that all the galaxies, they stay on the same line, almost. So, just to say any other quantity changes by factor 10 to 3, 10 to 4 in a galaxy. The only quantity, physical quantity that you can put in a galaxy, which remain constant, is this, the central density profile. And this comes, from studying different kind of objects of different luminosity. So at this level, this is something which has to be found. Of course, there is not even in particular cases of pure cold dark matter scenario. And so now I can finish this. It's important to detect the dark matter because, this is of course one other part which I will start from tomorrow. So it was one important things at the beginning in the 90s at least, that neutralinos, so the world dark matter, had a great advantages. One of the great advantages was the fact that it was, detectable in different ways. So, and the first one is the director. So if you let the direct detection, so we are enveloped in one dark matter halos. So in this room there are 0.3 GeV or centimeter cube mass of dark matter. Of course, I don't know how much. I suppose that one has 1 GeV, the mass of the dark matter. So in any centimeter cube there is 1/3 of dark matter particle. So in 1 meter cube there is you do the math. So the number of particles is very, very high. Of course, they interact very, very low in this scenario. So the level, so what you do, you prepare a very big, I will say, detector. If you say that sometimes it's made by, it is argon, for instance, in some cases, but then it is prepared by chlorine or other things, and the dark matter pass through, interacts, then there is a sort of, let's say, push, and the particle which has been pushed then makes visible, or because it radiates, or because other things. And this is very, very simple. I don't want to enter in this, but what is interesting is that for neutralinos, so for a particular kind of theory, the cross-section is the one which you can really obtain measurements. Okay? So it's possible to constrain very, very carefully the particle which is called comes from standard, I will say, one can say, I don't want to get the superstring, okay? But could even be a level of superstring, then supersymmetry. Supersymmetry, you have neutralino, and which is the particle, which is the supersymmetric particle, which is the lowest mass and the most stable. And then the cross-section is miraculously similar, able that if you build something, a sort of detector as is possible to build, you can detect several of these events every year. So, and this has happened since 30 years ago, but of course, although, as I say, you have, as I shown before, then you have a dark matter WIMP, which interact with the standard matter target, and then you have or ionization or photon emission or some other methods, and then you get the fact that you observe this. then what you get is nothing, okay? So there is not. But what is interesting in neutrino, which is very, very interesting because in other particle, in neutrino, other kind of particle don't have, is that there is a theory already ready. So there is the theory. These are the points, okay? So these are the points. And this theory comes from first principle, and the main shot will be in this direction. So therefore, you have that since 10 years ago, then the best cases, they were ruled out. These are the exclusion plot. Now we are at this level, okay? So this is, I showed before. And what is interesting is that the time passes, this goes down. Now we are a limit, which is the maximum limit that you can have, because then there is another phenomenon which will take over, which has nothing to do with the dark matter. So, but detection is zero, so you don't get. At this point, this one, so the direction on the ground in experiment, like for instance at Gran Sasso Institute, and they exclude the presence, okay, of a neutralino, for instance, which has, the characteristic that people think from the theory. And this is just one way, because I said this kind of particles are very, very, miraculous in some sense, because also another effect, which is their annihilation in a galaxy. Of course, this particle, as I said, they interact at the level of cross-section of 10 to minus 26 centimeters square between baryons, but they also annihilate when you are very, very, very dense, okay? So, and the galaxy is so big that especially if you go and you look in the position where you have most of that matter, and in this case for lambda CDM in the center of the galaxy, okay? So therefore you should see. It is another coincidence, no? Because not necessarily you could build something, or you could see to the telescope the emission of the annihilation. This is possible. If the dark matter is the one which we believe, we could see a signal from our nearby galaxies, and for instance, this gives the power that comes, and it's interesting that when you want to measure how much will come from a galaxy, the light will depend on nuclear physics, will depend on astrophysics, and elementary particle physics. But what is interesting to say that look at one of the dwarf galaxies that I showed before, I should find the signal. No way. And in fact, these were the prediction about 10 years ago, and the result is nothing. Okay, sorry. Okay. Was just the last my the talk. So the result is nothing. So we have seen, we have put our telescope in all nearby galaxies, and the limitations are very similar to the one which we found for the direct detection. Moreover, this particle does not exist also for another thing, to CERN. When CERN they have found the Higgs boson, contemporaneously they should have found many other supersymmetric particles. And they found nothing, so it means the supersymmetry now is completely detached to the cosmology. So if exist at a very, very high temperature, they have nothing to do with the dark matter. This is absolutely now the situation. Of course, dark matter is not only WIMP, this is clear. So I'm just talking about the main, but I think that I have also shown how this theory has a lot of advantages. It's possible to simulate, no? It gives unique result, it gives prediction in any case, and it can be really tested and attempted to find in laboratories. So therefore is a theory which not easily to be discarded, okay? So this is clear. But at the same time, honestly, so students don't believe the mantra that called dark matter is the dark matter theory, dark matter candidates, because at this point the people are thinking and maybe they are ready for a change of paradigm. And this is from what we get from galaxies and what we know, okay? So then the idea is that 10 years ago we thought that dark matter in studies in galaxy helped to know how galaxies form, no? Okay? And also eventually the dark matter profile, also the nature of dark matter. Now, or at least to exclude the nature of dark matter. Now the situation is much more complex. So we see that dark matter has a lot of properties at galactic scale. I didn't show today because today there is a more, for students also, so the students must be known, they are the first steps, okay? So if you follow me tomorrow, then I will say why the justification of what I am saying. But what I've shown in this lecture was, I think, at least interesting, no? So in the sense that you find a lot of relationship from observations, but you don't find any similar thing from theory. Okay, so then, the take-home message is dark matter is, I would say, if dark matter has to be in every galaxy, then we have found this. Okay, but we don't know if dark matter is really in every galaxy. This is the first thing. Second, if the dark matter has to have what we think from theory, then we have a disappointment. Dark matter does not believe at all in as we thought. Okay? And so the third message is that maybe, we will see tomorrow, we have even to change the paradigm. So, no? Because dark matter in the first 30 years has been studied in this way. I know the particle, know what is the particle, and from here I go to observations and then to anything. Now I think that the number of particles are run out, so in a sense the kind of particle that can be, they are not anymore possible, and so everything changes because we are outside physics. So therefore, if you are outside physics, then you have to start from observations. So now the idea to take more importance to observations is much more, is very, very important. For 30 years, the observations were the final proof of a theory. Now, the observations are the first step towards the theory, because it's not said at all that dark matter phenomenon, that is a phenomenon, realize is what is behind. Not necessarily is the most important theoretical adventure. Okay? Then it could be very banal, very trivial thing, and the theory around dark matter could be indistinguishable by other hundreds of theories that they are similar but different parameters, for instance, or different aspects and so on. And until now, we were very lucky because neutralino, they had incredible advantages because they had a lot of very, very good things. They made them really the best theory. It was a theory which was so. But when you started with neutrino, sterile neutrino, you start to have a particle which not everyone will agree. A very good axioms, again, you have this. And then stop it. We don't have any other particle which will come from first principle, almost everyone, in which I theoretically written say so, everyone follows. There is no finished. Then when neutralinos are abandoned, nothing. You must start from observation from zero. Okay, this is the take message, and if you want to know more about this, follow tomorrow at tomorrow. Okay, I finished.
So we have time for a few questions.
What is the mass of the neutralino?
The neutralino that they like is 100 JeV. 100 JeV, the neutralino 150 JeV. From, let's say, this is, if you go with the TeV mass, is not anymore related to the supersymmetry.
Well, maybe you'll go into more of this tomorrow, but as if dark matter weren't mysterious enough, as you've highlighted, there's been, as you know, some interest in recent years in trying to find a solution which simultaneously says something helpful about dark energy. Do you have any position on that? Do you have any view of what might guide us towards?
Okay, so the main that I could see it at the moment is the evolution of perturbations. So, this evolution of perturbation in cold dark matter is not much, no? The interaction between dark energy and dark matter. But just if you start to have a dark energy, no, rather than lambda, no, and the dark matter maybe interacts something like that. So I could see so we should not rule out this. Also, okay, this is one, but could be.
Right. And I suppose philosophically that helps with what some people think of as another problem, which is the kind of why now problem, if the dark energy and dark matter are coupled in some way.
Exactly. If you enter this, no, I agree. I agree with it.
More questions? If not, take time to follow.
Okay. Yes, my God. Okay. The microphone, yes.
Está en algún bolsillo, por favor. Sí, está, ¿no? Ahí, donde quieras, en algún bolsillo. Okay. ¿Listo?
Okay, so we are going to continue with our fifth seminar that is going to be given by Jorge Mastache from the MCTP in Tuxtla. And he's going to talk about Bose-Einstein condensates as candidates for dark matter.
Okay, well, thank you for the invitation. So I'm going to talk about scalar fields and a lot of the topics that already Professor Salucci talked about. Sorry. The outline of the talk is going to be like, I'm going to talk about a little bit of the fiducial model of lambda CDM. And in particular, I'm going to focus on the core cost problem that, like I said, Professor Salucci already talked a little bit about. Then I'm going to introduce the Bose-Einstein condensate that we work with. And this condensate we tested with rotation curves, and we are going to present the conclusions. So lambda CDM model is, I think that you should already know what consists on. So we have a very, very complex model right now and the understanding of the evolution of the universe. So we already know that the universe must start in a very hot and dense spot. And we have an exponential expansion, and then we have the CMB. We go through something that is called the dark age, then large-scale structure formation start, and arrive today. So we are not going to talk about a little bit of the details of the model, but I'm going to focus on the observations that give a strong prediction of dark matter in particular. So, sorry, I have cough. Well, sorry? Thank you. The strongest evidence of dark matter comes from like CMB, the cosmic microwave background radiation, which is the first photon that could travel through the universe. Along with the CMB came polarization of the CMB, came lensing of the CMB. This is also here are also the baryonic acoustic oscillations, which behind these two, this is the same physics of the perturbation of the of the CMB. The other observation, very strong observation, is the supernovae, type 1a supernovae, which gives us how fast the universe is expanding. And another kind of observations which are more astrophysical observations came from galaxy cluster and the dynamics of the galaxies, the rotation curve of galaxies, but also the Lyman alpha first and the large scale structure. Like I said, I'm not going to talk about a lot of the details of these observations, but this is just like a reminder that all of these observations predict some kind of need for more than baryonic matter, which is like the dark matter. So, in particular, we are going to test the model that we are going to present with galaxy rotation curves, like Professor Salucci already introduced. Sorry? Okay. Paul already talked about a lot of the details of the rotation curves. So, the fiducial model concludes that the universe, the content of the universe is around 68% of dark energy, 27% of dark matter, and only 5% is baryonic. So, unveiling the nature of these two components of the universe is really, really important right now. So many works around the lambda CDM model has been going through the recent years, and I'm going to talk about the problems that lambda CDM model has, and it has to be with with some controversy with with n-body simulations, and compared the results of the simulations with the observations. So we are able to do very, very large simulations that may take a little bit long computational time. And we are able to predict how much of substructure in galaxy kind-like structure we can have. And so we can study the substructure that are related to the galaxy size structure. So we can count the substructure around Milky Way kind of galaxy in the simulations. And the simulations predicts that we have to have like around 10,000, the order may change from simulation to simulation, but it goes like from hundreds to thousands of substructures around a galaxy of the size of the Milky Way. So when we observe substructures around our own galaxy, our own Milky Way, we only found of the order of 10 substructures which are the satellite galaxies. So this is one of the problems of that we already have in the lambda CDM model. The other one is the Korkas problem, which came also from simulations. The simulations tell us that the dark matter profile in galaxies, that's around galaxies, it has to be very Cosby. Sorry. Just like the number one black and white profile, and also another result from rule. But observation actually prefer profiles that we say core, and we say that is core because the central density profile of the halos are constant. So, because the n-body simulations and observations do not coincide very precisely, we call it the Korkas problem. So here this alpha is the slope of the density profile. So profiles that are Cosby usually have this value of -1 or -1.5. And we usually core profiles goes to 0 because, like say, this implies that we have constant central density dark matter halos. So I have to mention that the solution of these two problems have like two branches. One, it has to do with baryonic interactions. And I'm not going to go through the details, but I will just mention that if you took some of baryonic interaction like supernova feedback or active galactic nuclei feedback, we can explain or at least less I kind of explain some of the problems of the lambda CDM model. The other branches is to change the nature of the dark matter, actually. Thank you. So, the most famous profile that came from n-body simulations for dark matter is the Navarro black and white profile, which is this one. There are more profiles, the kind of the Moore or or some other. But the important thing is that when R goes to 0, this goes like to infinity. So these come from n-body simulations, and these ones come from phenomenology, in the sense that observation seems to prefer this kind of profiles. So I'm going to talk about a little bit of the dark matter candidate that we study, which is like a relativistic bosonic gas. Sorry. And it is not new that relativistic bosonic gases has been studied in order to be interpreted as dark matter. And it's also known that this kind of candidates can form stable structure around compact objects, and also quasi-bound states may exist around black holes. So with this idea, with the idea that black holes may be contained in every galaxy, we may study that quasi-bound states of the relativistic bosonic gases in galaxies may form stable structures like the halo surrounded galaxies and could dominate the dynamics of the galaxy rotations. So we know that the Klein-Gordon equation for complex test scalar fields is given by this equation. And if we assume a potential of this kind, where this new term is related to the mass of the boson gas, this other term is related to the self-interacting potential, scalar field. And we work it in the spherical symmetric space-time. We came around with the dynamics of the bosonic gas. So, for instance, this metric is just the Schwarzschild metric with this definition of f of r, where alpha is just given by this relation. And the relation between the parameter of the mass and actually the mass of the gas, of the bosonic gas, is given just by this relation. So actually here I'm showing you three of the three parameters of the model, which is the mass parameter, the interaction parameter, and this one, which is going to be related with alpha, which it has to be, which is related with the mass of the black hole in the center of the galaxy. So we propose a solution to the Klein-Gordon equation, which is of this kind. And the Klein-Gordon equation reduced to the Gross-Pitayevsky equation, which is this one. And using the Thomas Fermi approximation, which only tells us that the kinematical energy is so much less than the potential energy and the solid interaction energy. This is, we ignore this term. We can reduce the the equation for the boson gas. And so if we ignore this term, we can able to solve for this other parameter, which we identified like the density profile, the density of the boson gas. And actually the solution is very simple. And the solution is of this kind. So In addition to the three free parameters that already present, we have this one, which is the frequency of the of the scalar field. And this is the profile that we are going to study as the candidate of dark matter. So, as a review, these are of four parameters. Mu is the parameter of mass, the term of mass of the boson gas. M is related to the mass of the black hole. Lambda is the self-interaction parameter, and omega is the frequency of the field. So these three parameters came only from the particle theory. And this one, the mass of the black hole, is only the only astronomical parameter that can change from one galaxy to another. So how does the density actually look like? It looks like this black curve. So the red curve is Navarro-Frank and White, which goes to infinity as for small radii. Burkett and isothermal profiles, which are core profiles, go to a constant value. And we are kind of like in the middle. This is the density of the boson gas. And as you can see, it doesn't go to a constant value. Actually, it goes like to 0. And I'm going to explain later why. And this it has to be with the Fermi approximation. It is not valid for radii close to 0. And actually also for very large radii, the Thomas Fermi approximation is not valid. So let me explain a little bit more of the potential, because the potential is going to give us all the interesting physics for the dynamics of the boson gas. So if I ignore this term, I can simplify the potential as these two terms. For small radii, the first term is the one that it dominates the dynamics of the potential. And for large radii, it indicates like 1 over r to the 3. So only for values of alpha over r, similar to 1, are going to be the interesting cases where we can form quasi-states for the boson gas. And for instance, if I take r to be 1 parsec, this alpha, which is related to the mass of the black hole, I'm going to get the mass of the black hole of the order to 10 to the 13 solar masses. So okay, so this is to give you a little bit of sense of what is going on with the physics of the boson gas. So right now, I'm going to take any value of mu, and I'm going to solve for the maximum and minimum value. I want to solve for these 2 points for the potential, because the maximum value of the potential is going to give me the maximal bound for the mu, and also the minimum bound. So if I only take the derivative of the potential equal to 0 and solve this equation in order to get the value of r, I'm going to say r plus to this one and r minus to this one, to the minimum of the potential, I can solve it with this simple equation, solving this equation numerically. And actually there is a three point that comes from the trivial solution to f equal to 1, which is equal to say that the potential tends to the value of mu squared. So solving for r plus, which is given by this solution, I put the bound, the maximum bound for the mu, where the value of the potential evaluated at this R is going to give me mu max, and the value of the potential evaluated in R minus is going to give me the definition of mu, the minimum value that mu can take. And here I put 0.95, only because if I take this value to 1, it's going to make no sense physically, because I'm going to have like a point Bose-Einstein condensate only in 1 point, so I'm going to take this value to be a little bit more bigger than mu, the minimum value of mu squared. So actually the Thomas-Fermi approximation is constrained in this shaded area. It's only valid in the shaded area, because otherwise the potential is going to take negative values. So in order to see if the galaxy rotation curve actually can be explained with the bosonic gas that we are taking and with the Thomas-Fermi approximation, we have to solve for these two values of R, with R min and R max. And we have to make sure that R max actually has to be bigger than this biggest observational value of the rotation curves. So in order to solve for these two values of R, we only have to take the potential to be equal to omega squared. So it will define the potential well where the bosonic gas is going to be formed. The Bose-Einstein condensate of the bosonic gas is going to be formed. This is going to be the quasi-bond state of the bosonic gas. It's going to be valid in this region only. So, as you can see, this is the reason why we cannot get valid, well, the approximation, it is not valid for R going to 0. One of the interesting solutions is that when omega tends to the value of mu, the value of R max tends to infinity. So the closer is the value of omega to mu, the bigger are going to get R max. So for instance, if omega and mu are really, really close, so close that this difference is less than 10 to the minus 5, R max is going to have values of 10 kiloparsecs. And actually 10 kiloparsecs, it is not enough for all rotation curves galaxy data. So we have to have smaller values for these two parameters. So just like a review of what I said, the potential evaluated in R plus and R minus are going to give us the values of mu max and mu min. We have to have the constraints between these two parameters. It has to be smaller, less than 10 to the minus 7, so we can have R max large enough to explain rotation curves. The mass of the black hole, the central black hole, it has to be of the order of 10 to the 13 solar masses. And the only parameter that is left is the value of lambda, which it has to be between 10 to the minus 50 and 10 to the minus 90 in order to reach the magnitude of the velocities, of the observed velocities. So, like I said, mu is given by the by the particle physics, also lambda. The mass of the black hole is the only thing that can change from galaxy to galaxy. And the value of omega, we're going to fix it because this difference actually is very, very small and we cannot, well, constraining numerically is very hard. So we fix the value of omega, taking this relation. Well, we also make sure that R max, which is the place where the quasi-bound state of the bosonic gas is valid, given the Thomas Fermi approximation, it has to be greater than the maximum radius of the observed galaxy rotation curve. So we can integrate the density that I show you, that I show you here, here. We can integrate this density over the volume and get, and get the mass as a function of the radius, and we get all of these terms. But actually, taking a look at all of the terms, we can see that these two terms are actually negligible, because the value of these two terms are very, very small. And we kept with these three terms. And as you can see, this one is positive, and these other two terms are negatives. This one is going to be dominated at very small radius, which is this line. This one is the term that goes to as the logarithmic of R. This other term is going to dominate us at a very large radius, which is the blue dotted line. Well, this one. And actually, this is going to be the term that dominates at the interesting radius. And as you can see, it only goes as R to the square. So if you compute the velocity of this term only, you are going to get that the velocity, it has to increase as the square root of R. So if you remember from Keplerian dynamics, the velocity of any object, massive object, it has to decrease as, the velocity has to decrease as R to the minus the square root of R. I say it correctly? Yeah. So the velocity given for this mass is actually the counterpart of the decreasing of the Keplerian dynamics. So I recall, or I will grasp, I will say we are neither of them. The slope of the profile that we get is actually this, is given by the blue line. So as you can see, the slope is only equal to -1 in a certain rate, in a certain region. Below this region, this is not valid approximation. Above this region, it's also not valid. This one is given like a core profile. It goes to 0, so this means that we have a central density profile. And this is kind of like a Navarro fine and white because it goes to -1. So we have a very different profile. So our mass model depends on we take values for the gas, for the bulge, if it exists, for stars, and for the Bose-Einstein condensate given by the bosonic gas. So our velocity increases like R to the square root of R. This is the mass-to-lag ratio, and we have two values of the mass-to-lag ratio, one for the bulge and one for the stars. And this is only to convert from luminosity to the mass. But we take this constraint for the bulge, and there is some studies that approve this kind of approximation. We did it only to reduce the number of free parameters, because these two are free parameters of the mass model. And we take data and take the best parameters that reduce the chi-square, which is defined as this one. No? It's only the difference between the value of the model predicts for certain values of the free parameters, and it compares with observations. So we took data for the Spark catalog, and the Spark catalog, it has like 170 something galaxy rotation curves, but we only use galaxies that fulfill these like constraints, if you can say it, for the data. So we only took galaxies that have large number of data points, above 30. The observation of the galactic center, well, it has to be very close to the galactic center. It has to have a smooth rotation curve, maybe non-bulge, and it have to have a very nice circular rotation curve. So I will show you two galaxies that we constrain. This is given for the Navarro-Fargan White, and this one is given for the back. So I put it just in front of the Navarro-Fargan White, so you can see the difference. So it's Navarro, and this is the Bose-Einstein condensate, the Beck. So Navarro, Beck, Navarro, Beck, Navarro, Beck. So as you can see, there's a clearly difference between this line, which it has to, this line is related to the rotation curve only from stars. And it's different because of the mass-to-lag ratio value. So Navarro-Fargan White tends to suppress the contribution of stars, while the Beck tends to increase the contribution of the stars. So this line is related to the Bose-Einstein condensate, and this other line is related to the Navarro. And as you can see, the final rotation curve, which is the blue line, are really close and really similar. And this is another galaxy. Again, this is Navarro, and this one is Beck. Navarro, Beck, Navarro, Beck, Navarro, Beck. So the conclusions are similar. Navarro tends to want less contribution from stars, while the Beck wants a little bit more from stars, the contribution to total rotation curve. And again, the total velocity curve is this one. So as you can see, we have a little bit of difference. And how we do it, compare it with Navarro-Fargan White? Well, actually, we didn't beat Navarro. And here you can see the value of chi-square from Navarro, the value of chi-square from our model. And all of these points, well, the points that are in between this region are galaxies where we can say that we can compete with Navarro. But all of these points that are outside of this region is where Navarro actually really beat us, really beat the Bose-Einstein condensate model. And only, we can say only two galaxies, well, like 1.5, we do better than Navarro, Frank, and White. We also do Bayesian statistical analysis, where if the points are inclined to the left, it prefers more Navarro. If are inclined to the right, it prefers more to Beck. Here in the middle, we are like, we compete with Navarro, but we didn't beat Navarro. So Navarro actually, the data actually preferred the observations actually preferred Navarro, Frank, and White profiles more than Beck. So, but actually, even if the observations preferred the Navarro, Frank, and White profile, we did not do a bad fitting at all. And why did I say that? Well, this is the review, the summary of the constraints of the three parameters that we have. This one for the Beck. So we get a value for the mass parameter around 5.4 parsecs, 1 over parsec, sorry, which is related to the mass of the bosonic gas, which is of the order to 10 to the minus 23 electron volts. And actually this order for the mass of the bosonic gas is in concordance with other theoretical analysis and other observational constraints for the bosonic gas as dark matter. The self-interaction parameter, it has values of 10 to the minus 19.1, which is related that actually this gas is really to be taken as an ideal gas. The mass of the black hole, in average, it has a value of 10 to the 11 solar masses. And the mass to light ratio for the Beck is this one, and the mass to light ratio for the Navarro, Frank, and White this one. And like I said, Navarro, Frank, and White tend to suppress the star contributions more than the Beck model. But the interesting thing is that, and that's the reason that we said that we didn't fit so bad at all, is because if we take the ratio between the Beck model and the Navarro, Frank, and White, we take this value. So we did it worse than Navarro, but we cannot say we did it really bad. That's what I'm saying. So, do we have a supermassive black hole, or what does it mean that we can have a supermassive black hole? So, what can I say from this point is actually we have two observations from Abel 85 and Holm 15A, where they actually observe central black holes of the order of 10 to the 9 to 10 to the 11 solar masses. So we are in the upper limit of these observations.
I have to interrupt, please.
Yeah.
You are talking about spiral galaxies, not there. And the black hole in spiral galaxy is very, very small.
Yeah.
And it is never, at least 4 order of magnitude smaller than the one in you find.
Yeah.
Moreover, you have shown before M33 galaxy.
Yeah.
Okay? I know because I studied my galaxy, this one. The black hole is 0 at the center.
Yeah.
Dark matter is a lot. Core, a lot. So you cannot say it's a problem on this, rather than the square. The problem of the mass of the black hole is a problem. You should find 10 to 8. So solar masses.
Yeah.
Not 10 to 11.
Yeah. Yeah, that's right.
Say that we are. No, it's problem. So you are ruling out if you will find a way to get to the mass of the black hole less. Because especially in galaxies, okay, in spiral galaxies, this is something people maybe don't know. But there is a very, very big difference between the big black hole in our galaxy and in elliptical galaxy where there are quasars and so on and so on. In our galaxy, the mass of the black hole is 10 to 6 solar masses. And we are one of the biggest galaxies, the spiral galaxies. So therefore, if has to be the black hole, is important, you must find a way where the dependence has to be different from one to the other. Because it could be a good idea. I am not saying a good idea, but the mass doesn't fit.
Yeah, and there is a problem that we actually acknowledge, and there is a caveat for our model. And we have to take a deeply understanding of the model. So the next step that we are taking to take is like to take the weak field approximation for the for the metric and include sorry the gravitational potential of stars, bulge, and gas in the center of the galaxy, and see if we can't make the mass of the black hole to be a little bit less. It's like taking elements of the gravitational potential, give it only to the black hole, and give it to the stars of the bulge. So, but like I said, we haven't done this, so it's like the next step to this model. Also, we are thinking also in taking soft gravity effects for the bosonic halos, and see also if this can help to to minimize the mass of the black hole, and also take into account effects caused by rotation of the black hole, maybe, I don't know, maybe also reduce the mass. So this is our conclusions. So the bosonic and condensate model comes from first principles in the sense that we deduce the density equation from the Gross-Pitayevsky equation. We take the Thomas Fermi approximation, and we are able to describe galaxy rotation curves quite well. We assume that we have a black hole, and this black hole, well, the mass of the black hole that we get, it has to be really, really big. The average of the bosonic of the bosonic gas is of the order to 10 to the minus 23 electron volts. And well, this is just a recent article that we published with all of the details that we just talked about. So thank you.
So we have time for questions. Yes, please.
In your approximation, you consider the number of particles for density for pi?
The number of particles for the bosonic gas?
Yes.
No. No, but we know that it increases as we get the self-interaction parameter bigger. So it is related to the self-interactor parameter.
Just to follow up a little on Paolo's point, so you've made the assumption that the black hole is the only compact central object that condensates.
Yeah.
And then, just to make sure I understand right, that led you to the conclusion that you had an unreasonably high mass required for that black hole.
Yeah.
So the first assumption, is there any other way that you could have the condensation of the boson cloud without having a black hole in the center?
Yes, they are.
I
They
would
could
think so.
use the bulb, as I said, they could use
Exactly.
the disk. I told them one
Okay.
month ago.
Sorry, well. So would you agree that maybe it's the first assumption that was too strong, that actually
Yeah.
don't need to have the black hole as the mechanism.
Yeah, we acknowledge that problem.
That sounds to me, as you say, it's an interesting idea, and it's just that you need to have the mass in the centre around which the boson cloud condenses.
Yeah.
Just a comment. Remember that the Thomas Fermi is just an approximation, and it's not valid for all the values you provide. Okay? So, for this approximation, so I will have to take this into account. If we want to get a more realistic mass of black holes in the center of the galaxy, we have to solve the entire equation of motion. Okay? So this is the first step. And we have to take into account for the other phenomena of the set. So this is the first step will be on tested the Thomas Fermi approximation, which is very simple. This is an algebraic solution of a very, very complicated equation, right? So the first step is fit quite well, right? So we have this problem with that hole, but we can.
So the reason for that may be the breakdown of the Thomas Fermi approximation. That's another possible explanation, I see.
The next step is to calculate the density, taking into account the entire equation. And let's see what's happening.
Yeah, another comment around this idea is that also this idea came from first principles, in the sense that we have a theory that can explain this kind of behavior, and also with a very, better statistics for a good one. I mean, we are less than 1 sigma, and we have this kind of behavior for this, at least this spark sample. Okay? And well, this spark sample also have like 3 kinds of galaxies. So yes.
Okay, one thing about NFW profiles. So the failures of NFW profiles, as I said, is not on the chi-square. The chi-square is only one aspect. The problem is when you fit with this model, you find unphysical masses.
Yeah.
And you find the unphysical mass toleration, as you are seeing some of them. So the failure, so to compare the NFW profile is what we want to win easy. Because, everyone model is better than NFW. So even model, so you should look with phenomenological model. If you are able to be similar to the one which have the same number of parameters in the phenomenology, rather than NFW, because okay, then is nothing to do better than NFW. If you say that you don't even do better, it's tragic, because I see every model does better. F over R does much better, MOND, any strange method is model that does better than NFW, because it's very, very bad. In spiral galaxies. So
Okay, thank you.
Okay, just let me remark that this is a very, very simple model. Right? You have a black hole, and you have a test here. That's all. There's no you don't have to go to numerical analysis to get the density and so on. It's very, very, for first principle, this is the right